Ladies and gentlemen, let's begin the show. So yesterday, we are talking about arrays, linear search, binary search. We show that linear search and binary search are actually correct in the sense that we can use them to find the target item in the array. Or if there's no such item in the array, we can correctly tell you that there's no such item in the array. So it's correct. And we also sort of claim that binary search is not as good as, linear search is not as good as binary search in the sense that linear search takes a linear scan over the whole array to determine whether an item is in the array or not. And binary search is much better. It takes what we call log n time to determine whether an item is in an array or not. So why do we say that a linear time algorithm is not as good as a log n time algorithm? And this is the first topic to be covered in today's lecture. After that, we will cover sorting algorithms to make an array in a sorted way such that binary search can be applied. So this will be the two topics of today's lecture. Let's start with showing that a log n time algorithm is better than a linear time algorithm. Now, to show that one thing is better than the other thing, we first have to have a way to quantify exactly what do we mean by the running time of an algorithm. In this case, we use this big O notation to help us do the analysis. So we say a function belongs to a function family, a class of function family, under this big O notation if it satisfies this condition. What exactly does this mean? So in mathematics, it means that given two functions, fn and gn, if we can find two constants, n0 and c, and if this variable n is greater than this constant n0, if variable n is greater than constant 0, then we can guarantee that anything that's greater than, when n is anything that is greater than n0, we can guarantee that c times gn is always at least as large as fn. So we are saying that, essentially we are saying that gn grows at least as fast as fn. That's the definition of big O notation. But what exactly does this n0 and c and all these constant and all these larger than relationships? Let's take it a step at a time, and let's slow down and starting from the basics. So we say this is the definition. If fn belongs to this class of gn function, then it satisfies this equation. This is just basically just a copy of, well, not basically, this is exactly a copy of what we got on the slides, except that now I copy it into a Word document. So to simplify the discussion, let's not worry about the constant c so far. Let's just focus on n0. So far, so good? Let's look at n0. Now, what do we mean by fn and gn? Let's look at a few examples. Suppose we look at the first f1n. So f1n is just one example of fn. There's a few more. f1n is just n minus 1, f2n is n minus, 1 million. And then f3n is 0.09999 times n. So a little bit smaller than n, essentially. Now, gn here, very simple. Let's just say gn is n. So it's just a simple linear function, gn equals to n. Now, based on this definition, we want to find, can we find this particular number of n0 such that when n is greater than n0, fn is always less than or equal to gn? So, can you tell me, for f1 function f1 and g, f2 and g, and f3 and g, which would be the value of n0 that will satisfy this equation, inequality? Yeah?
Yeah, well, in this case, any value of n0, but if we assume, well, n0 is greater than 0, so let's say 1.
Right. Okay. So apparently, I'm a psychic. I already predict that this would be your answer. So if n0 is, for example, if n0 is 1, then for any value that is greater than 1, we always guarantee that f1n is smaller than or equal to gn, right? Easy. And it's always like that because we know that n minus 1 must be smaller than n. How about the second one? What would be a good value of n0? Yeah? Yeah? So, you know, I'm just so great. Last one, whole class. What would be a good value to make sure that f3n is smaller than or equal to gn? 1. Ta-da! My best magic for the class. All right. So, easy. So we find this value, n0 equals to 1, and we can guarantee that. So we can pretty much safely to say that, in this case, we found a function gn that grows at least as fast as fn. So gn is like an upper bound in terms of the growth rate of fn. Very good. Look at a couple more. How about we introduce another function, f4n? And I haven't changed anything yet. I haven't bring in the c yet. So it's still only one variable, or one constant, n0 in here. Can you find me a number for n0 such that I can satisfy f4n0 must be less than or greater than gn0? 0. Unfortunately, there's a requirement that says n0 must be greater than 0. Looks like a really long number. What would be this number here? Anyone? Anyone at the back? No? Let's give someone else a try. Anyone, please? How can we guarantee that f4n is smaller than or equal to gn? Nobody says anything, and that's actually a correct answer. No, we can't do that. How about f5n? Here it's very much similar to this f3n, except that now it's a little bit larger than n. I suppose we can't do that either, right? But if you think about it, in terms of the function growth rate, is n minus 1 and n plus 1 really that different? If you plot them on a figure, they will be exactly the same curve, same straight line, except that they are off by a little bit, right? In terms of the slope, they are exactly the same. If you compare 0.999n and 1.001n, it's also very similar. They will be all of them at the origin point, and then one is slightly steeper, the other is a little bit slower, but the difference is very small. We don't care about that small difference, and to cope with this small difference, we throw in C. Now you got a additional constant to satisfy this. If I tell you that now it's not just n0 but also c, can you give me a choice of n0 and c such that we can guarantee that f4n0 is less than or equal to cgn0? What would be a possible solution? To simplify the discussion, let's keep n0 to be still, for example, just 1. So what would be a good choice of C? To remind you, f4 is just, f4 function here is just n plus 1. So what would be a good value for C? Yeah?
Like
10? Okay, you break my magic. 10 is a good call. You can go as small as 2, right? Because now we double gn. And obviously, gn is just n. Double that is 2n. 2n is very easily to outgrow like 1n, right? So similarly for this one, what would be an answer? Yes, 2, right? But we can go even smaller, just as small as just 1.1, just slightly larger than this 1.001. I don't even need to do 1.1, I can do 1.0001. And I can still outgrow this. And that's the metric in here for this big O notation. Essentially, what it defines is a upper bound on the growth rate. And in constants, we don't care. So whether you got 1.001 or if you got 100,001, we can always bound it with this ON. Because of this constant in here, if your Fn is like having a large constant, we can absorb that using this constant C. And that's the concept of this big O notation. Now, if you sort of extend this logic, suppose now we got Gn equals to log n. And so Gn is log n, F4n is still n plus 1, and F5n is like, doesn't really matter, we can revert back to 1.001n, right? So F4n is n plus 1, F5n is 1.001n, Gn now is log n. Can you find a constant n0 and c such that we can guarantee F4n must be less than or equal to Cgn, and similarly for F5n? Can we do that? Now we really can't. Even if we drop in this constant c, we cannot guarantee that, because we know F5n and F4n, they are what we call linear functions, and they grow faster than these logarithmic functions, right? So that's the idea of big O notation. Because of this, we can't say that a linear function belongs to a O log n function. But on the other hand, on the other way, we can do that. If Fn is log n, and then Gn is n, then Fn still can belong to Gn, because the one inside of big O notation is the one that grows faster. As it's an upper bound. So for this big O notation, it's an upper bound. Remember that. And that's the idea of this big O notation. Make sense? Mathematically, it looks very complex, but ultimately, it is just an upper bound. So this is in words. This is what it says in this big O notation. If Fn belongs to OGn, and then there's some sort of a lot of mathematical words to describe this, and that's enough. I don't want to repeat that again. But in English, this means if Fn belongs to Gn, it means Fn, this Gn here, grows at least at the same rate or a faster rate than this Fn. So again, big O notation is upper bound. Similarly, there's actually a few other notation that defines the lower bound, and then this a strict equal in the sense of it bounds the lower bound and then bounds the upper bound, and then the two class complexity classes are the same. We can do a bit of analysis in here. Let's see. So Fn now is not just like 1.001, and we change that to get a bit larger constant. We make it 2n. And we say that F1n still belongs to ON. So n here basically means Gn equals to n. So n here is basically just a linear function for Gn. So we say that F1n belongs to this one. But in the meantime, F1n also belongs to all of this. Why? Previously, in all my examples, the Gn part is very simple. Gn is just n, or Gn is log n. The Fn part can be quite complex, like a simple linear function could be like n times 0.001 or times 0.999. But this time it's kind of on the opposite. We change the Gn, and the Gn part becomes more complex. And we say that F1n also belongs to all of this. Why? Any thoughts? Yeah? Can you speak louder?
Like
to the class?
If you take the limit of F1
Okay, are you from mathematics? Your background, I mean. Yeah, okay, very good. So mathematically, that's the reason in computer science or English terms, because all these terms, they grow faster than just a linear function. Because 2n minus 1, even though there's a minus 1 term, doesn't really matter because all these are constants. We throw them away. Constants, we don't care. Throw away all the constants, and we say that, so both are linear, and this still bounds there. And similarly for this one, throw away the constants, and then n plus log square root n must be also a bit larger than n, right? So this also grows faster than this. And this one, similarly, n times log n must grow faster than just n. So based on this upper bound definition, all of this can bound f1n. Following the same logic, even if I have a rather complex f2n, this will also hold. Now, this analysis will then becomes a bit more complex. Now, typically, how we derive the complexity class for a function would be, let's throw away all the constants. All the constants do matter. So throw away that, throw away that, throw away that. So here, what's left is just n and plus square root n plus log n. So among n and square root n and log n, which one grows the fastest? N grows the fastest. All the rest doesn't matter. Just throw them away as well. So in the end, for this f2n, its sort of closest complexity class will be just on. And similarly, for these terms within this big O notation, we could also throw away all this stuff. They don't really matter that much, can throw away them. This one you can't throw away the log n, even though log n is a relatively smaller term, but gives this a multiplication together. So you have to keep that. And for this one, this 2, even though it's a constant, you can't throw away that because it's a n to the power of 2. So you can't throw away that. So that's the idea. So far, so good. We can even make it more complex, but I don't want to sort of delve more time onto it. You can play with this one after class. So by this definition, this big O of Gn, this is actually a set of functions, not just one function. It's a set of functions whose complexity is bounded by this OGn. Now, as we just said, when we derive the complexity class of a function, even though there are so many different bounds, upper bounds of a function, we want to derive its closest upper bound. And to derive the closest upper bound, this is the approach. Throw away the constant and only keep the main part. And if there are multiple terms, for example, in here, if there are multiple terms, throw away the constant, and anything that is not as significant as the first term, throw them away. And so even though 2n times log base 2n obviously is still upper bounded by this 5 times n squared minus 3, this is not so tight as this n log n. And when we write the time complexity analysis, the result, usually we just write this one rather than writing something like this. Yes?
Are you sure we just wrote all the coefficients of the constant?
Yep. Just throw it all this. But some of the things you can't throw. This base 2, you can even also throw away that because we know log base 2n, you can actually decompose it into log n divided by log 2. So that's still a constant, you can throw that away. But if it's like n to the power of 2, this constant you cannot store away because that's multiplication. For multiplication terms, you can't throw away. All right, so that's this. And as we just mentioned, using this big O notation, it defines an order of different complexity classes. So based on this one, as we just showed, we managed to show that log n belongs to n, but n doesn't belong to log n, I mean in big O terms. So because of that, we successfully showed that if you have an algorithm that runs in log n time, it must be given large enough input, it must be in the end runs faster than an algorithm that runs in O(n) time. But on the opposite, you can't say that. And because of that, we successfully show that binary search is, strictly speaking, better than linear search in terms of the running time. All right, so far so good. And And that basically finish our first topic. Any questions before we move on to sorting? Anything at all? Or is it that I've done such a great job that you can't ask any question? Alrighty, let's move on to sorting. So we say that binary search is so great, but in order to make binary search work, we have to sort an array first. We have to actually learn one of the sorting algorithms, a sort of a variation of bubble sort, which is quite intuitive, except that in running time it's not so great. Actually, we have a figure to show you in terms of this running time stuff. So if you plot all these different sort of functions, like including like O1 log n log n square, 2 to the power of n, and n factorial, if you plot a curve in here, it's kind of like this kind of relationship. O1 here actually means a constant time algorithm. That means no matter what kind of input you have, I just need one single operation. Or I could use 10 different operations, for example, 10 comparisons. But as long as the number of operations I need doesn't scale together with the input size, then that's a constant time algorithm. Meaning that no matter how your input changes, I always take this amount of time. Even though this amount of time could be 1 year, still a constant time algorithm. So in this big O analysis, that hidden constant sometimes is a matter. So sometimes you've got algorithm that in theory is superb, but in practice it's not so great because the hidden constant that we store away is so big. But in terms of analysis, O1 is the best we can hope for, a constant time. And a bit worse than that is log n. You probably cannot show there's a little bit a green bar in here that's very close to the constant time. Log n time algorithms already very good. If you think about it, log base 2n, if n is 1 billion, what's log base 2n? You probably wouldn't know, that's just 30. If you have a binary search algorithm to search one item within 1 billion items, that only takes 30 comparisons. Almost as good as a constant time algorithm. Now, further worse than that is n, and then after that is n log n and n squared, and then 2 to the power of n and n factorial. N factorial is really bad. Actually, anything from this on, 2 to the power of something is already too bad. If you've got a solution that falls into these complexity classes, they are essentially not really super practical. Usually, yeah? Sorry? Yes, the green line here is very close to the constant time. Yeah, because log n times is already very good. Probably in practice, log n time solutions is usually the best we can hope for. And even if you got a linear time solution, it's already very good, except for a linear search case because the problem is very simple. If we end up in this zone, what typically we do is we do approximations. We sacrifice the solution's optimality or accuracy, but we want to go for a faster solution because simply algorithms in this realm, they simply do not work, do not scale in practical data. So this is the typical complexity class that you might want to familiar yourself with. Now enough that. Sorting. Now the bubble sort, the one with all these playing cards and all this demonstration, that's a variation of the bubble sort, and it actually takes O(n) squared time. It works intuitively, but if you have a billion items to sort, it doesn't really scale that well. So in the rest of the class, we're going to introduce, we want to try to introduce two sorting algorithms. One is still n squared time, but it's run in a systematic way, and the constant in there, the hidden constant in there is a bit smaller compared to the bubble sort. The other one, we actually can show that it can achieve n log n time, which is the best you can hope for sorting. If you think about it, if you want to sort a sequence, at least you need to go through them at least once, right? So if you want to make a sequence to be sorted, O(n) time is at least the bare minimum. You can't do anything better than that. Actually, you need to do a bit more than n, which is, it has been theoretically proven, the best you can do to sorting is n log n, if there's no special layout on the data. If there's special layout, obviously things differs a little bit. If you think about it, if you have an array that's already sorted, then all I need to know is just go through it once and make sure that it's actually sorted, right? So that you can get O(n) time. But in general, the best you can get, average, is n log n time. So let's first look at this insertion algorithm, which is still O(n) squared time, but has a smaller hidden constant. The next one that is supposed to be faster, well, it's faster, it's quicker, it's quicksort. Not surprising. So let's look at how insertion sort works. Now, the idea of insertion sort is like this. If you have an array that is not sorted, making it sorted is very difficult. If you have an array that is already sorted, now you just have another new item. You want to also put it into the array and make it sorted. That's a lot easier, right? So suppose I have a sequence of items, all these items. All of them are sorted. And now I have a new item I want to insert into this sequence that is sort of previously sorted. What do you need to do? You want to check, are you smaller than me? Are you smaller than me? Are you smaller than me? Oh, I got an item that is smaller than the new item. Stop, put it in here. The whole thing is still sorted. So that's a lot easier. And that's the idea of insertion sort. That's what you got the name, insertion sort. It assumes that you have an array that is already partially sorted or entirely sorted in some sense. And you just treat the items as arriving items and put it into it and keep the whole thing remain sorted. So the insertion sort algorithm works as follows. So first, if you have an array that has only one item, is this array sorted or not? It's sorted, all right. So I got an array with an item 12. It's sorted. Now I have to move on to the next item. Now this is the new item, and I have an array that is sorted, even though this array now is super short, only one element. I have another element. So what do you want to do? If I want to sort of make sure that to put this new element into this sort of partially sorted array to make it sorted, what I need to do is to compare this new element with the last element that is previously sorted, right? So I'm going to compare them. And print 34. Great, one comparison, done. Now I have an array that is sorted, except that this array is super short, only two elements. Following the same logic, let's look at this one. Ooh, lucky us. Compare this one with that 34, that's it. We don't have to compare with 12, right? That's the part where we have the save. In the bubble sort, you have to go through everything, compare every pair. But in the insertion sort, this helps us reduce a bit of the comparison. We only compare up to the first one that is smaller than the new one. Next one. Finally, this appears to be something that we need to do actually a bit of sorting. So compare this element with the last element that is sorted. Apparently, 43 is less than 55, so we need to cut it out. And we need to do a bit of swapping. So 55 got moved to the right. Continuing with the process, now I need to compare with the previous element before 55, which is 34. 34 now is smaller than 43. Done, put it in. That's it. Continue the process. 66, we don't need to do anything. 61, we need to do one swap. You got the idea? I don't want to bore you and repeat the whole thing, but we can do a bit of analysis in here. To show you the whole two array, it looks like this. So let's focus on how many comparisons we need to find the correct position for one element. Now for the first element, we actually didn't do any comparison at all, right? Second element, we need at most one comparison. And the comparison is the one with the one in front of it. Third element, the maximum number of comparison we need is 2. We need to compare with the 2, right? And the third one, the maximum is like at most 3 comparisons, and we will find its correct position, and so on and so forth. So essentially, for each element, one more element to the right, we need at most one more comparison. So the first one, no comparison. At most 1, at most 2, at most 3, 4, 5, 6, 7, 8, 9, 10. in total, how many comparisons we need in the worst case. So essentially, we got a sequence, and we want to sum up this sequence, right? What's the sum of this sequence? 55, right? Now, here, if you look at this analysis, what does 10 mean? Number of elements, right? Actually, -1. We got 11 elements. 11 here is actually the number of elements. So then, what's the complexity given the big O notation for this function? N squared. So, in terms of big O notation, insertion sort doesn't really help too much. Still N squared, just like bubble sort. Make sense? Let's look a little bit about its implementation for this insertion sort algorithm. Not this one. Oops. Oh, unfortunately, I lost my insertion sort. Let me repopulate that. Right, I'm basically just trying to run a piece of code to execute insertion sort process. This is implementation of insertion sort process. The array is still the same array that I showed you in the Excel table, right? So I create an array, and then I'm going to call this sort int array function, which is an implementation of the insertion sort algorithm. So creating the array, setting that we got 11 numbers in this array. Now this is the insertion sort trick. We got an array A, we got n elements in the array, and we need 2 looping variables to help us do that insertion process. So for the insertion process, if you look at the demonstration in here, essentially we'll need a loop to go through each of the elements, right, to find the right position for them. We need the outer loop is to go through each of the elements in here, and then we need to find a right position for them. Now this looping variable I will start from the left to the right. We could start from the 0th position, but not necessarily, because the 0th position we said is one single element is already sorted. So we don't need to worry about that. So the first looping variable I will go from the second element to the end. Now the inner loop will in charge of, given one element, I want to find its correct insertion position. And that insertion position will start from the item. We'll start from the current location and going through to the left. So the second looping variable j will start from I, and each time it will do j minus 1 to look for one element ahead, and to see, are you smaller than 66? Are you smaller than 66? Once you find an element that is smaller than 66, the looping variable j can stop. That's what's being written in this part. We got a first for loop that goes through starting from the second element, because the first element is considered already a partially sorted array. And the inner for loop will go from j equals to I minus 1. This is just the immediately preceding element of the current element you want to insert. And you want to see the immediately preceding element, is it smaller than the current element you want to insert? And you will keep going to the left, through the left, and you want to keep comparing, is it the current element already greater than the previous element? If the current element is already greater than the previous element, we stop. Only if the current element is smaller than the preceding element, we continue and do a swap. That's what this piece of code is saying. I want to demonstrate this animation process a little bit to help you understand this process a bit more. I'm sure you know how insertion works. This part is just to show you how to translate the idea of insertion sort process into a C code implementation. I also added additional pointers. These pointers does nothing. It's just for demonstration purpose. For implementation, you don't need this line in here. All that it does is just tell you this is the number that we are looking at right now. So I got a pointer PI, points to this is the number of concern at the moment. And apparently for this one, we already know that the previous one is already smaller than that, so we don't really need to do anything. And now we are just moving on to this one. And the same will happen again. We don't really need to do anything for it because the preceding, immediately preceding element is already smaller than that. Now would be the first instance where the immediately preceding element is not smaller than the current element to be inserted. At this moment, I'll need to do a swap. And to make that swap happen, we know if we call it int swap function that Shannon demonstrated, we have to go for 2 pointers. Otherwise, the swap wouldn't work. So now I created another pointer. This again is for demonstration purpose only. I got 2 pointers. One is the current one to be inserted. The other is the one immediately preceding it. We want to do a swap. And this is just the swapping process. I'll just quickly skip. So the swap function is done. I got the swap finished in here. And the process will continue. This time, we will find that the element immediately preceding the 43 is already smaller than that. So this part will finish. And we'll move on to the next one. The pointers here stay like that because we haven't really changed their value later on. They just preserve the previous round of results. That doesn't really matter because in the next round of processing, we'll update them. So apparently 66 is greater than 55 already, so we don't need to do anything. And then we move on to 61. And then now, again, we have a pair that we need to swap. So the 2 pointers quickly jump to them and help us do the swapping. The same process applies. This time, the next one will be more interesting because we need to do a lot of swapping. So there will be 1 pair got swapped. And this, importantly, these 2 pointers pointing to the 2 elements to be swapped, they got updated properly to the previous pair. And we do another swap. And we got these 2 pointers pointing to the 2 elements to be swapped. They again also got updated properly. And so on and so forth. I don't want to bore you with the whole process, but you got the idea, right? So far, so good. That's insertion sort, and that's the time complexity analysis of insertion sort. Great, we actually run quite fast, and we got time to talk about quicksort. So insertion sort. Insertion sort is great. It actually cut down the constant part, the hidden constant part in the big O notation, big O runtime. But still, n² time algorithm, not so great. Next, we're going to talk about quicksort that is supposed to be super quick and reduce the running time from n² to n log n. How does quicksort work? The idea of this quicksort algorithm is like this. So in all those previous, like bubble sort or the insertion sort, every time we look at an element, or in every iteration, the whole iteration going through one whole pass of the array, we want to sort one element essentially, right? When you finish the whole run, every time you finish the outer loop, no matter for bubble sort or the insertion sort, we want to find the right position for one element. For quicksort, the idea is actually quite different. For quicksort, we take a more holistic view of the whole thing. What it does is in each iteration of going through the whole array, we try to do a partitioning of the array into three sort of partitions. One is sort of the median partition, and one is the smaller partition, one is the greater partition. Within each partition, the actual order, they are not actually ordered yet. But what we know is that all the elements in the smaller partition must be smaller than anything in the greater than partition. And if we're recursively doing this, each time we make the overall of the array more and more sorted in some sense. That's the idea of quicksort. So given an array, it wants to partition the array into 3 partitions. Now, how do we partition into 3 partitions? We have to select a a standard of what do we mean by median. And to select that, we use what we call a pivot. And there are many different ways to select the pivot, and that actually has some quite an impact on the final algorithm time complexity. And we'll talk about that later on. For now, just allow me to pick the first element of the array. I'll pick the first element of the array, and I'll say this will be my standard of the median. And then I'll try to push this one actually to the middle part. And anything smaller than that, I want to keep it on the left-hand side. Anything greater than 33, I want to put it to the right-hand side. Now, I have used a few different colors to represent different things. The blue part represents all the things in the array that is smaller than 33. Apparently, there's nothing yet. Now it's still empty, right? So, and this number in here is just the array subscript indexing. So this means A-1, because actually this is before the array. Nothing is in there yet. This is A0, A1, A2, A3, and so forth. This is just a subscript indexing of the array elements. Now, for the greater than partition, I use a green color to represent it. And similarly, at the moment, I don't know which are the elements that are greater than 33 yet, because I haven't seen anything beyond the first element. So I'm going to just have to assume that the whole thing equals to 33. And gradually, I'm going to grow the blue part, and I'm going to shrink the green part until they hit. That's the idea. And I'm going to have 3 variables to help me keep track of these things. So for animation purpose, I can keep changing the color. But in a C code, you can't really say like which part of the array has different color. You can't do that, right? You have to have some sort of variable to keep track of what's going on. Now, I'm using 2 variables to keep track of how these blue parts and the green parts grow and shrink. The yellow color in here keep track of the first element that is equal to the pivot value. So at the moment, because we pick the pivot to be 33, so the first element that is equal to 33 must be element 0. And all the rest, I'm going to assuming that they all equal to 33 until I'm proven wrong. All right. Similarly, I got another variable called first GT. This is the first element that is greater than 33. So far, only this element is proven to be greater than 33, which is a non-existent imaginary element. So far, so good. Now, we need to go through the elements in this array to shrink and grow the 2 different partitions. Next is the variable. Essentially, it's a looping variable to help us go through the whole array to make sure that we grow and shrink this green and blue part properly. So next is now at 0, and apparently we don't really need to do it too much, because A next, meaning that A0 equals to this pivot value. The looping and comparison process is always taking one element in the array and compare it with the pivot value. So now we are comparing A next with pivot. And A next apparently is just pivot. So all that we need to do is that, all right, confirmed. This is actually the equal partition. This element belongs to the equal partition. So let's just move on. So if we move on, that means we change the value of next to 1. And then I'm going to look at A next, meaning A1. So I'm going to look at it. And 12. Apparently 12 is smaller than 33. So we know by our definition, we need to push the element smaller than the pivot to the left. And to do that, what we need to do is do a bit of swapping. And swap here is a variable that helps us to do the swapping. And how do we do this swapping? The swapping will be done with the current element, between the current element and the first element in the equal partition. And the first element in the equal partition is this one. Why does it have to be the first element in the equal partition? Even though, suppose that later on, we somehow grow this equal partition to be this section, and you find an element that is smaller than the 33 pivot value, then we can't swap this smaller value to any of these equal partition elements. It has to be the first one, right? Otherwise, you're going to create less than, equal, less than, and equal. Then that's not good. That's not good. So it has to be the first one. So these two got swapped. But how do you know which one is the first one? Well, luckily, we have this first equal variable to keep track of which one is the first one. So you're going to do a swap. Now, after the swapping, we need to do a bit of update. Apparently now, the first equal is not this one anymore, right? Because the less than partition has grown. So we have to grow this one a bit. And because of that, the first equal have to grow to the right. Make sense? And similarly, we are going to move on to the next element to look at it. And now we are looking at the next element in here. 55. 55 is greater than 33, right? So how do we do it? Well, following the same logic, where do you think we should, which one do you think we should swap this 55 with? We know all the things that are greater than the pivot 33 need to push to the right. But where do you think this 53 should be pushed to? To the right, to the left?
To my right.
Yes. I know it must be pushing to this direction. But which would be a good place to put it in? Well, you might think that, well, 55 is already greater than 33, maybe it's enough, let's put it in there, and we got 3 elements, that's in order, we're happy with it. Not so great. If you just keep it in there, later on it will cause complications. We have to push it somewhere. Which would be a place that if we push it to, it's guaranteed there's no complication later on. You want to give it a try? 10. The 10. Yes, move this one to the 10. But how do we know where is the 10? Which of these variables tells us the 10? The first greater than. We need to move it to the one that is one element smaller than the first greater. Because we say this is the first greater we found so far, and now we don't know what about this yet. So why don't we just move it here? Because I don't know whether it's really greater than the pivot or not. But I know this one must be greater than the pivot because we already checked that. Right? Now once we have done that swap, we need to shrink the greater than partition. And to do that, essentially we are just reducing the first greater variable by 1. Now here's important. After we've done that, in the previous step, every time we process one number in here, we always increase next, right? We are done with one number, next. That's what next means, right? In this case, we cannot go to the next yet. We have to stay. And the reason that we need to stay is because we haven't checked this one yet. We just blindly move it to the front. And we don't really know whether it's smaller than or greater than or equal to the pivot. So next stay. But the interesting bit, very important to observe in here. Previously, each time every time we process a number, we increase next. Or next doesn't increase, but the first greater got reduced. That's very important. So it's either you grow from the left or you shrink to the right. Each time, no matter what, you always reduce the search space by 1. And this is a guarantee that after n elements or after n iterations, the next will meet the greater. So that's a guarantee to show you that if you do this kind of, so this is actually called a partition process. If you do this partition process, only O(n) times needed. You only go through the whole thing once. You don't need n squared, you don't need n log n, just once. And this is very important to help us show that for quicksort, it's just n log n time. And the n here is coming from this process. You only go through the whole thing once. and you can partition it into 3 partitions. So that's this one. Now, moving on, let's look at one more. Let's look at this one more element. So now we got another smaller than element, and following the same logic, we say whenever we got smaller than element, we need to swap it with the element that is pointing to the first equal, right? So we want to do a bit of swapping. So 19 got here, and 13 move up. And after that, the first equal must be increasing, and the next can move to the next. So we again grow this smaller than partition a bit more. Continuing with the process, now it's like a new case where we got a value, a pivot value, new element that equals to the same pivot value. In this case, we don't need to do any swapping. All that we need to do is just keep going with the next, and let's just continue and move to the next one. And the same process applies. And after a whole round of processing, this is the result. Actually, I changed the elements a little bit such that we have a few same value of pivot to show there's actually a middle partition. We got a smaller than partition, we got a equal partition, we got a greater than partition. Now, once this process is done, in the second iteration, the equal partition, we don't need to do anything about it because we know they are equal, right? And they must find its right position already. We don't need to do anything about it. And for the things that we don't need to do anything, I'm grading them up. We don't need to do anything about it. Now we need to do the same partitioning process for the first smaller partition and then for the greater than partition. Right? We need to do that. And for smaller than partition, we again apply the same procedure. We take the first element as the pivot and partition it into 3 partitions. And in this case, I'm not going to repeat the whole process because it's going to take too much time and we are kind of finishing already. But we already know that there's only one element equals to the pivot. There's nothing smaller than the pivot, so there's no blue segment in here. There's all the things, they are green segments. But you can see that the order of these elements got swapped a little bit. And that's because when we go from the left to the right, the elements that are greater than the pivot, they got all the way to the end. So they got a bit of shuffling. And we got 3 elements in here. Again, we take this one as the mid one, and apparently we got one element that equals to 61, the pivot. We got one element smaller than that, one element greater than that. So in the second iteration, that goes to the whole thing. Again, we found this partition for each of these 2 partitions. And after that, after this process, again, we have 2 more elements where the positions are confirmed. Right? So we know 12, after this second round, we know 12 must be the smallest one because there's nothing smaller than it anymore. So keep it here. The 333s are here. 61 is here. And the only thing remaining are these few values to be sort of further partitioned. And repeating the same process. Repeating the same process. This time I'm picking 29 as my pivot, right? Because this one is done. So these 4 elements got left. This is actually a case that shows the partition process is not always so great. If you are unlucky, you can end up with a partition that only help you find a position of one element. The other things, you have to repeat the whole thing. This is actually a bad case for quicksort. This one is a good case. This one is a bad case. This one, again, is a very good case. We partition it exactly evenly on the 3 partitions. So if you end up with a bad case, what will happen is you have to process still in this partition the whole thing. And this time the pivot is 29. And again, unluckily, all these elements, they fall into the smaller than partition. So again, after the whole thing, we only save one element. But for this partition and this partition, because they only have one element already, so they are just choosing as a pivot and this part is sorted. So after this process, we found another 3 elements that are already done. And we continue with the process, and we can get it done. Now, the beauty about this quicksort algorithm is in each round, even though later on when you look at the implementation, it's a recursive function, it looks very complex, but important to know that in each round, you process one element in the array for exactly once. So each round is O(n) time. How many rounds? Here we got 5 rounds. And if we are really lucky, and every time we exactly partition it into 3 equal size halves, then we can reduce that to log(n) time. So log(n) rounds. But in here, because we are not so lucky for this first half, so we got a bit more than log(n) rounds. But that's kind of a constant factor before the log(n). We don't care that too much. We still claim that this is log(n) time. So that's quicksort. And that's pretty much it for today. We'll talk about sort of the more analysis and the code implementation about this quicksort after class. Question, we can talk about that after class, right? Because I don't want to keep the whole class too long, right? So that's it for now. And in today's class, we talk about efficiency analysis, we talk about insertion sort, we talk about quicksort, and next week we are going to talk about analysis of the quicksort and its code. And then we're going to start a new topic. That's all for today. And for the mixed semester test, I'm going to send out an announcement over the weekend. That's all for now. See you next week.